Okay, getting an early start on this, I guess. So, good morning. I know that the title of this talk is a little bit of a mouthful. A lot of this is going to be about why this is important as much as what this means to say in many parts. How can it be concise? What do we mean by concise in this context? And what is more complex than deterministic context-free, and why does that matter, are all questions that I hope to answer. So if you've been following at all the research that's been coming out of language theoretic security, which is an initiative that was largely spearheaded by Sergey Bradis, Meredith Patterson, Len Sassman, and several others, you might have noticed that earlier this year we published a taxonomy of essentially root causes of parser vulnerability. So we took a little bit of beef with existing sort of CWEs around how we deal with broken parsers in applications. This is gathered mostly from existing research in the area and is essentially just a systemization of previous papers, all of which are available at langsec.org. The one that I've highlighted today is actually the one that's given us the most pushback, and so I thought that I'd take the opportunity to explain on the record exactly what it is that we mean by this, why it's important, and why it can be done. It follows very closely, as I mentioned in a previous talk on this, very, very, very few parser vulnerabilities actually fall into just one of these categories. Most of them have multiple connotations. And in particular, this concept of an input language being greater than deterministic context-free is very much associated with shotgun parsers. So again, if you've been following our research, it will become readily apparent why this as well as that are critical. So why exactly do we want deterministic context-free? Well, deterministic context-free is a class of languages. It kind of falls in between on the Chomsky hierarchy. It's right below context-free. It simply means a context-free grammar that you can parse and generate deterministically. This particular class of languages is the most powerful class of languages for which we can solve a number of problems. General equivalence is one of the main ones here, which means that we can tell that two parsers, or in fact, more formally two grammars, but in effect, in practice, two parsers, are equivalent for any of these classes of languages. Another point is that they're decidable, which means that in a finite amount of time, or at least a known amount of time, we can figure out whether a given string is in the language and valid, or out of the language and not valid. And then the third point, which is what I'm going to cover today, which is that they are actually sufficiently complex for general use. If you go any higher than this and you end up with more complex languages, which I'll get into in a little bit, then it becomes impossible to decide, especially decidability and general equivalence. And we find that on the whole, these tend to be the locus of bugs. Now, it's important to remember as well that this refers to the language that defines your protocol, your data interchange format between various files. This has absolutely nothing to do with what language you program in. Of course, nobody is advocating that you use non-Turing complete programming languages for general purpose programming. That would just be silly and it wouldn't help. This is mostly about making sure that we don't have a lot of parser bugs, and this is actually really important. I'm sorry to recap so much, but we did a short survey of OpenSSL bugs in the preceding year or so before we published our last paper, and we found that over 2/3 of them were actually parser bugs and not cryptography bugs, and we wondered, surely there must be something that we can do to see to it that the locus of bugs in a project is actually things that are related in some way to what it's trying to accomplish, not ancillary things for which there are general purpose methodologies. So what we proposed is a software engineering methodology that allows us to prevent these sorts of vulnerabilities from occurring in the first place. And I mean, again, the thing that has been most contentious and difficult to implement is this concept of deterministic context-free, because simply not a lot of people understand why that is, and it's important that for a piece of security to be usable, it be understood both by security practitioners and by developers exactly how you implement it. So in any event, this is what we think of as a deterministic context-free language from the practitioner's standpoint. From an academic standpoint, it's very different, but it does essentially reduce to these things. Essentially, the key feature that we're looking for is that validity of a protocol message is only ever determined based on a context that's established along some nested hierarchy. What this means is that you can't say, well, parse the whole document and then correlate these two pieces within the document that do not nest, and then see that they match up for your validity. You can't do that. It turns out that when you do that, it becomes impossible to prove most parsers. You'll just have to believe me since this is only a half-hour talk. It also means languages that we could process with a deterministic push-down automaton, which is another one of those annoying formalisms. What that means is, given a finite amount of state and a stack that is potentially unbounded, although no real stack is, given those two things, you can parse this protocol. You don't have potentially an infinite accretion of state that you might assemble that can't be put onto a stack and popped off orderly. It means a language that is similar in complexity to matching balanced parens, but no more complex than this. So for example, XML tags, as long as those XML tags are properly nested and don't have cross-references and external entities and weird imports of document type data. Maybe XML is a bad example, but certainly JSON does tend to follow this. I'll get into a little bit more why that's not enough, but these are the features that we look at. Also, it happens that BNF and associated grammars, EBNF and ABNF, also tend to generate languages that fall within this class. So if your protocol can be specified that way, as with an RFC, you're fairly close. One of the things that I'd like to highlight there as well before I continue is that a lot of the times when we do specify protocols using a formal structure like ABNF, we tend to include little angle bracketed remarks in there that say, check some of that. It turns out that this is okay, and that's one of the things I'll be following in the coming slides. So to recap again why this is important, previously I just did a search for bugs that had to do with cycles, unbounded recursion in protocol parsing. We found these. It also happens that the hijacking of the Ethereum DAO falls into this. There are many bugs, and the one thing that all of these bugs that are cited in this way have in common is that they have structures like that which you'll see there. It's possible to generate a document in which there is, sure, some overarching elements, but within it there are 3 non-hierarchical elements which cycle in this way. And things will happen. Like, for example, Adobe's PDF parser will happily try to generate infinite index simply because something refers to its parent, which again refers to its child, and it just keeps going back and forth. So it is this structure that is responsible for lifting our protocol away from, at worst, deterministic context-free into, at best, context-sensitive, which is one level above in the Chomsky hierarchy, and all of the formalisms around proving that the parsing of it will ever terminate or can be determined valid or not, or can be equivalent to go out the window. You simply can't do them. So we propose in language theoretic security that this lifting is kind of a problem in much the same way that one of these thunderstorms will flip an airplane over if it's small. These sorts of things will tend to cause your program to crash. So we wonder as well, with respect to language theoretic security, why it is that there are so many bugs in software. Well, no. I see a lot of grimacing. No, it's simply not the case. It's not because programmers are careless. It's not because they're foolish. It's because more often than not, the specification that they're trying to implement sets them up for failure because it's things like too ambiguous or too complicated, and it has these problems where it's not amenable to formal verifiability. And it's also not amenable to mechanical verifiability of the type that we hope in the future will be provided by static code analysis tools, which is why we're proposing this as a CWE. We also wonder, all of the previous examples that I cited a couple of slides ago were all about denial of service attacks. It's not just about denial of service attacks. I'll mention again the Ethereum DAO hijacking example, whereby general recursion in a known Turing-complete smart contract language was essentially used to steal all of the money out of an Ethereum blockchain contract structure without any computer system being able to see that this was going to happen, or any human really being able to anticipate this in the general sense. It was bound to happen eventually. We also saw in many, many, many papers published, weird machines. A weird machine is a term that I believe Sergey Bradis coined, which has to do with kind of an unintentional structure of computation that exists within a program, tend to have a hand-in-hand sort of relationship with exploits. So what we're trying to do with respect to this recommendation of keeping your parsers to no more complex than deterministic context-free is to minimize parser complexity. We're taking the Turing machine away because we don't want to give the attacker a Turing machine. And our parser is our first line of defense. Again, with respect to avoiding shotgun parsers, it means that we have a very discrete boundary. In comes the input. And if the input is untoward, the parser says, no pasaran. We're just going to reject this. So, it's a tall order. Reducing the complexity of our input languages is something that has, it's a very strong countercurrent to what we spent most of the 90s doing. When we started introducing a lot of active content like Flash and like Adobe Acrobat and like JavaScript, immediately we found that our content became a lot more rich. There was a whole world of things that we could do with XML and DTDs and infinite extensibility of X509 and all of this stuff. But we find that now that we've developed our engineering practice more and more, there's a common kernel of things that we tend to see occur over and over and over again in protocols that we definitely need to do. And then there's all of these other things that represent huge complexity and have in the past led to vulnerability, which is why I chose the examples that I just chose of how it is that we kept lifting ourselves above this. People ask me this a lot. Ultimately, the answer is, well, kind of. We have a lot of walking back to do. And this is just one part of that. I hope that in the future, people will propose new protocols that follow this recommendation and avoid that type of complexity, avoid general purpose computing that you can just kind of foist on other people before they can tell whether it's right to do it or not. So, of course, these notions, you see here the Postel principle, all kinds of other things. We have to be careful to ensure that although we can't get rid of them today, we don't perpetuate these problems. Ubiquitous abstraction and dependency injection are another one I'd like to specifically call out because they generally lift you to Turing completeness. So yeah, like these things have continuously been problems and they will continue to be problems until we solve this specific problem. And this thing where the input language is above deterministic context-free is actually a common recurring theme in all of them. I already went through that example. But essentially, again, if we don't do this, it won't be amenable to computational solutions. So here's the standard of proof for whether we can tell if an input language is safe based on this criterion alone, remembering that there are 6 others in the previous work. We know that all of the idioms that are within it are within deterministic context-free, and that there is closure under the accretion of these idioms into the protocol, so that the way that they're used doesn't end up creating some kind of implicit cross-reference or something that would lift the language. The idiomatic fields, to simplify that proof, may occur only once in the context, and the data upon which it relates to for validity is within DCF. So in other words, if it does not in and of itself create those patterns that we cited in one of the previous slides, and it can be computed by a finite state machine that has a stack, then we're all right to use it. So let's briefly see if there are a few things that we can find within deterministic context-free. I promise that I'll keep this short. These are essentially proofs, but I've tried to make them comprehensible without too much formalism. So the first one that I would like to point out is protocol state. Protocol state is something that we run into a lot. Almost every protocol has state. And we wonder, well, it's very hard to write a regular expression, or it's very hard to write BNF that gives the protocol state. But we can do a quick proof here to show that, in fact, protocol state is perfectly acceptable and retains your access to the tooling that we can develop around these types of simple protocols. So we let P be a stateful protocol. We include the context that it sits in. Context-free is, in this respect, a little bit of a misnomer. It simply means the context is only hierarchical, not that there is no context at all. So we can take this context in which the packet is being parsed and treat it as though it were an encapsulating element. Then we can simply do this. We can say, we'll draw up a state machine using our existing protocol state machine from these previous states S, and then we'll simply add the validity of the message to this. We'll construct a new state machine that essentially adds arrows to a reject state for all of the messages that are not valid given our current server state, and there we have it. We've just shown by construction that it happens that this is just me citing exactly how you do that construction. Draw those arrows in a formal way, we can see that having protocol state alone isn't enough to lift the language above even potentially regular. It is just a finite state automaton because the protocol state machine is a finite state automaton. If it's not, then unfortunately this doesn't work. It's important to note that this didn't even change our actual protocol specification. There is a large family of protocols that do not need to be revised with respect to this recommendation. We need to only zero in on those particular things that would lift the language. So if, for example, the protocol state machine were able to force you to look back an arbitrary number of packets to see previously whether your current element is valid, rather than trying to keep that protocol state finite within the machine, and it didn't allow you to put that into a stack-like thing, rather it intended that you keep an infinite lengthy index, then it would not work. And we would hypothesize that that would be a locus of bugs. We see as well, with respect to authorization, this is my next example, by the way. Authorization is not specifically guaranteed to be deterministic context-free. And in fact, I have a number of examples where non-deterministic context-free authorization has resulted in authorization bypasses. These examples are Android master key and PKI layer cake. Both of them very different. In the interest of time, I'll only discuss Android master key. If you recall, this was the vulnerability whereby an Android app is essentially a zip file, and it contains a manifest. There were two different parsers. One of them looked aside in one direction forward to the first manifest, and the other one looked in direction to the second manifest. The two parsers had two different functions. The first one essentially was to determine whether the manifest was valid, and the second one to determine whether the package matched the manifest. So the attacker could trivially simply generate or take a valid manifest, tack it onto the front, and then make a new invalidly signed manifest that actually corresponded to what was in the jar, tack it onto the back, and it would validate. Does this structure sound a little bit familiar? Because, yeah. So if we ensure that our authorization follows certain properties, we can avoid this type of problem from an engineering perspective, and it just won't happen. Again, a little bit of formalism here. Feel free to read along, but essentially what I'm saying here is that if we ensure that the authorization fields that convey the proof of authorization are in some way in a hierarchical relationship with, an unambiguous hierarchical relationship with the thing that they are authorizing, then there can be no potential for confusion. This is an exercise in explicitly specifying what it is to which this authorization applies and seeing to it that this authorization is specifically associated with the thing to which it applies. Because again, if you have those cross-references, you can't really show what's going on. So this is also going to come up when I talk about checksums later. The third one that I see most often is an objection to length fields. People say, well, how on earth do I construct a finite state automaton or a stack machine that deals with my length fields? This, it turns out, is not too terribly difficult. There's a device that we use in proving these things out called unary arithmetic. It's basically just a tally. 5 ones is 5. That might begin to look a little bit to you like matching balance parens. When we match balance parens, essentially what we're doing is we're creating a stack. We push the paren onto the stack when we see an open paren. When we see a closed paren, we pop it off the stack and see if it's the same. If it's not the same, we reject. If we've reached the end of the input and the stack is empty, then we accept the message. And that is just a formal way of matching brackets. No actual computer would do this. You would use counts. But nonetheless, that's how we do these proofs. So matching balance parens in unary arithmetic, it turns out, is exactly the same as matching characters in a message to a unary tally established by the length field. So as long as we see that the length field is in a hierarchical relationship with the thing to which it applies, then we can validate the packet. This, it turns out, is one way that we could do something like avoid heartbleed. You might recall that heartbleed was essentially a length field validation attack problem. If there had been a parser somewhere in the beginning that had said, I'm going to now keep a tally and see that I get as many things out of this message as it claims that it has in it, we wouldn't have had the problem in the first place. It would have said, no pasaran, you're gone, bye. So we've just done, by the way, a proof by reduction here. We've shown, formally, without doing really a lot of math at all, that it happens that length fields are within our definition of deterministic context-free, QED. You might, as I mentioned, want to implement the stack as an unbounded counter, or better still, you might want to be very explicit about your specification and bound the counter. This is an interesting point because no actual machine really is able to implement a full pushdown automaton. Lacking infinite stacks, it's simply impossible. A very common bug that I've seen, unfortunately I don't have a reference for it handy, is one whereby a language will fail to specify that a given length is signed or unsigned at 64-bit, or worse still, it will demand that, that the length field be up to uint 64 max. This is kind of a nightmare for Java programmers because they have a bound to signed 64-bit integers, and when you have that problem, a lot of people take shortcuts. So you can see how this also ties into the need to couple it with an explicit specification of the language for you to really gain the benefit of it. But both of these things are required. You must also do this, and then bugs like Heartbleed will be a thing of the past. The most complicated example that I have of this is checksums, digests, and signatures. And this is where I look, again, I mentioned when we're specifying protocols in RFCs and ABNF, usually we just say, signature goes here, don't worry about it in the context of this formal description of the language. Well, that's all well and good. I don't especially want to draw up a regular expression that validates is the correct MD5 sum of what preceded it either. Technically, it's possible to generate a regular expression that does very simple things, though. Like, for example, one that matches divisibility by an arbitrary natural number for all numbers of radix r. That is to say, if you told me, give me a regular expression that matches all binary numbers that are divisible by 7, I can actually draw that. I'll get into the reason that that's possible in a little bit, rather than boring you with the regular expression. It's actually miles long, but it does work. The characteristics that we're looking for here in this proof are simply these 6. It has bounded computation time, so we know it'll terminate. This means that it's not got a Rice theorem-based proof of Turing completeness. It means that we look for the fact that it's guaranteed to be both complete and either right or wrong. This again means that it's decidable. So we see that anything that is undecidable cannot fall within the definition of deterministic context-free. Happily, that's why we chose it. We see that it can depend entirely and only on specific input. That means that it has that hierarchical relationship that I was talking about before. Simply the fact that it's tacked onto the end, or maybe it's somewhere in the middle, but for purposes of computation replaced with all zeros. As long as this process is fully deterministic and fully decides in advance to what it is going to apply, we're actually fine to use it. So again, doesn't care about input semantics is basically the same thing. Constant output length simply means that it will be within regular. If it had an unbounded output length, then it could be at best context-free simply because it would not have bounded state. And then composed of mathematical operations in finite fields, which is what I was just mentioning with the whole divisibility by 5. The way that we construct that finite state automaton is basically by creating a machine that by adding and shifting computes the modulus continuously of whatever input it gets. And so if we bound ourselves to things that are composed of mathematical operations in finite fields, which is basically that, we can show that they can also be implemented by regular expression. We just don't want to implement them by regular expression. It's seriously enough to show that it can be implemented with a regular expression. So since we have this, we can actually do math in our programs, right? We can, as long as we keep ourselves to cyclic arithmetic like that, to arithmetic in finite fields, we don't need to go beyond regular, which is one level below deterministic context-free. As long as the computation looks like this, we're fine. We also don't need to go and specify detailed BNF representations of exactly how you compute an MD5 sum. A description of the MD5 algorithm that follows these 6 characteristics is enough. So what this means is, in conclusion, most of the idioms that you actually use and need that don't generate those structures, those cyclic structures that I was talking about before, and that don't cause your parser to do arbitrary computation, like the DAO hack or like parsing active documents, ransomware everywhere, you're actually going to be all right to not have a lot of bugs. So make sure that when you specify a new protocol, or when you have the opportunity to amend an existing protocol looking at HTTP2, most of the things that you use are the things that you need. Don't add things that don't follow this. It's premature ability. Features that lift the input language to context sensitive or above are almost always the loci of bugs. All of the examples that I was talking about before and many more that are cited in our other papers are directly traceable to the inclusion of complexity such as this. This is truly the embodiment of complexity is the enemy of security. So we find that the language theoretic's advice to keep protocols within deterministic context free is feasible to implement. It's actually not too far from the way that we do things now. There are only very few things that depart from this. And if you avoid things like this, it won't be a problem for you. So I'd encourage you to look at what this work is a further explanation of, which is a paper that we published earlier this November at IEEE SecDev, as I get everyone at a security conference to scan my QR code. I promise it's not XSS. And yeah, thank you very much for giving me the time and opportunity to do this. I'd be delighted to take questions, both now and as little does anyone know, there's a language theoretic security conference embedded at IEEE Oakland as a workshop, and we'd love to see you there. The CFP actually just opened a couple of days ago. Thank you very much. I'll open for questions if I have time. No questions. Okay. Yeah.
Do you have an assessment of how much work that would take versus what the... Can you basically do a paper napkin cost-benefit analysis for me?
Okay, so question essentially, did I just propose that we redo the whole internet, and can we do a cost-benefit analysis on that? Well, so we don't have to do it all at once first, but we've already started. So the cost-benefit analysis is largely being done for us now. We're seeing a lot of enterprises doing things like disabling active content in web pages by prohibiting the installation of Flash, disabling Flash plugins within browsers. We see a lot of macro disablement policies in Office documents. We see as well that the cost-benefit analysis is rapidly being done for us by those that fight against ransomware, because that is almost completely dependent upon Turing completeness in document formats. So unfortunately, I don't have a cost-benefit analysis right here, but I hope that the anecdotal evidence of every time we see one of these bugs, and they all do seem to fall within this problem, we immediately begin mitigating it by disabling large swaths of features from the internet that we put so much work into developing. I would say that it will probably be extremely favorable when sometimes someone gets around to it. All right. Anyone else? Okay, I'll be around all weekend.